Welcome to the first presentation in this unit, Unit 10, called Chemistry Can Leave a Sour Taste in Your Mouth. It said, bad taste is simply saying the truth before it should be said. Mel Brooks. So, if you were to look at this particular presentation, number one, the goals are to define the characteristics of acids and bases, to use IUPAC nomenclature rules to name acids and bases, and to identify the strong acids and bases. So number one, what we already know from the previous unit, we know that solutes will dissolve in a solvent to form a solution. That's going to be particularly important because we're going to talk about things like dissolving HCl and where they're all going to be aqueous solutions. So we're going to assume that we're dissolving them in water. The concentrations of solutions is expressed in molarity. Now remember, molarity is a capital M and means number of moles divided by the volume in liters. So it's generally expressed in moles per 1 liter. And we also know that solutes dissociate in solutions. Remember, sodium chloride actually becomes Na plus and Cl minus in a solution. Next, we know from the lab that acids are sour and turn litmus paper red. Bases are bitter and turn litmus paper blue, and that acids and bases can mix together in what's called a neutralization reaction. So what's an acid? We know that acids are sour, and that's actually the origin of the name acid, comes from an ancient term for sour. We know that acids will turn litmus paper red, like you can see right here. This would represent an acid. We know that they conduct electricity, that they're electrolytes. Okay, which means that they are going to disassociate in water. We know they can be used to neutralize acids, and they can actually be used to react with a metal to form hydrogen gas. And you see that here with zinc mixed with hydrochloric acid, these little bubbles, and we've actually done this experiment. These little bubbles will actually move up in the solution and can be captured in their hydrogen gas. Okay, there's a couple of different definitions though for acid. We're going to start off with the most broad definition, and that's that of a Lewis acid. Okay, a Lewis acid is something in which that can accept electrons. So if you have something that's even something like let's say it's platinum 2 plus. Platinum 2 plus has the ability to accept 2 electrons. 2 electrons can come in and make this Pt with no charge. So this platinum 2 plus would meet the definition of what we call a Lewis acid. These Lewis acids are based on Lewis dot diagrams that we've talked about before. So if you have something that accepts the electrons, like you see when these two things bond, that would make this the Lewis acid. And that would make this, we'll later learn, the Lewis base. But more on that later. So a Lewis acid is based on the transfer of electrons. That is the most broad definition of what an acid is. Next we have the Bronsted-Lowry definition. Now this is a more narrow definition of an acid. Platinum, the example that we used before, would not meet the definition of a Bronsted-Lowry acid because it's based on the transfer of protons. Whenever we talk about a Bronsted-Lowry acid, we're talking about something that has to give a proton away. It has to donate a proton to something else. Since platinum doesn't have any protons, it has no protons to give away and therefore would not meet the definition of a Bronsted-Lowry acid. Next, we have what's called an Arrhenius acid. Now this is the most narrow definition, and this is going to be our working definition for an acid. So whenever we're talking just about general acids, we're going to be using the Arrhenius definition of the acid. Now you do need to know the other definitions of the acid, and you do need to be able to distinguish something as a Lewis acid or a Bronsted-Lowry acid or something along those lines. But this is what we're going to mean when we generally talk about acids. It's the most specific definition, and it is based on the reaction with water. Basically, you have to take something and add water to it, and then it has to disassociate in that water. So Arrhenius acids will increase the number of what are called hydronium ions in water. You can think of them as protons, but they're hydronium ions in water. Now, we have the all thumbs are fingers, but not all fingers are thumbs rule. So whenever you look at this, all Arrhenius acids, you can think of them in degree of specificity. Lewis is the most broad. Bronsted-Lowry is next, and then you have Arrhenius is the most narrow definition. So all Arrhenius acids are Bronsted-Lowry acids, which are Lewis acids. But not all Lewis acids are Bronsted-Lowry acids and are not Arrhenius acids. So because of that, you need to know them in terms of which is the most specific definition that you can apply to a certain substance. Now, there are some common acids that you deal with in every day. You have acetic acid, otherwise known as vinegar. You have carbonic acid, which is actually in your blood whenever you breathe. You have citric acid, which tends to be in things like lemons. A common acid used in chemistry is hydrochloric acid. It's also in some cleaners. And then you have phosphoric acid, which tends to be in things like Cokes or Pepsi or other soda products. And then you have sulfuric acid, which is used as an anti-corrosive. So it tends to eat through things fairly easily. And it's not just something that you generally see every day. So now, whenever you name acids, there's a couple of big rules associated with naming acids. And the most important thing is you have to know the polyatomic ions, because whenever you're changing something to an acid, you have to know the anion it's based on that. So for example, if you have sulfate, sulfate is SO4 2 minus. Well, if you were to name this particular acid right here, which is H2SO4, you name it based on the anion. So that anion is sulfate. So I come down here to this chart and it says 8. Well, whenever you have an anion that's an 8, it makes the acid an ic. So instead of sulfate, it becomes sulfuric acid. Now, if you would have had SO3 instead, well, that's still a -2 charge, so it would be H2SO3. But instead of it being sulfate or sulfuric acid, because it's an ite, okay, the ite goes to us. Those are backwards right there. The ite is going to go to us, and because of that, it's going to be sulfurous acid. Okay, and then finally, if it was just H2S, this is a sulfide. Whenever you have a sulfide or an element by itself, it becomes hydro blank ic. So you would have hydro, and then this right here would be sulfuric acid. So if you can see, the naming of the acid is actually going to depend on the anion. So you have to know your polyatomic ions. Whenever you classify acids, you can classify them as being strong or weak. And what determines whether they're defined as strong or weak is whether or not they completely disassociate in water. So for example, you see an acid here. We'll call it HCl. Okay. If you look, there are some H's and there are some Cl's that are disassociated from one another. But that right there is not the case all the time. These are still associated, this is still associated, this is still associated. So this right here would not consider to be a strong acid, it'd be a weak acid. In fact, because of that, it cannot be HCl, because HCl is what we call a strong acid. And it disassociates completely. None of the protons or none of the hydronium ions are actually attached to any of the anions. So because of that, we have a strong acid. Now the strong acids that we have is something that you have to memorize. These are the 7 that you're responsible for memorizing in this class. You have hydroiodic acid, or HI, HBr, HCl. So these 3 things are the halogens minus HF. HF is not considered to be a strong acid. So you have HI, HBr, HCl. Those are the ones that you're interested in. Then you have the 8s. Okay, you have sulfate, nitrate, phosphate, and then perchlorate. So because of that, those right there are considered to be strong acids as well. So you have the 3 that are the halogens, and then you have the 8s. And if you can remember those are the 7 strong acids, and you do need to memorize those. Those will come up. Okay, whenever you're measuring the strength of acids, you look at it in terms of pH. Now we're going to measure it with something called a pH probe. The pH probe is one of these devices that's right here that is used to determine the amount of hydronium ions that are actually in a solution. Whenever you do that, it's going to put it on a scale from 1 to 14, or 0 to 14. That 0 to 14 number that's going to come up is going to tell you what the relative strength of the acid is. So if you were to look here, you would see this is litmus paper. Litmus paper is another way that you can actually measure the strength of an acid, with the 0 being actually the strongest and the 13 or 14 being the weakest. Okay, so that right there is a measurement of the acid strength. Now we will talk more about the pH scale in the second section of this particular unit. But the pH scale does go from 0 to 14, where you have things that are very acidic versus very basic. And like we said, more on that in the next presentation. Now, name the 7 strong acids from earlier in this presentation. So remember, we have the 3 halogens. We have HCl, HBr, and HI. And then we have the 8s. We have nitrate, sulfate, phosphate, and the last one is perchlorate. So with those 7 named, it now says pick one and write an equation showing that it's an Arrhenius acid. So we're going to pick HNO3. When you have HNO3, whenever we're defining something as an Arrhenius acid, we're saying that when we add water to it, it actually disassociates. It becomes H plus, aqueous, and NO3 minus, aqueous. Because these are strong acids, we can say that this process is 100%. In other words, there is 0 HNO3 left when you put it in water. It is completely disassociated into H pluses and NO3 minuses. So now it says draw mechanisms showing how HCl meets the definition of each of the acids. So the first one is easy. We already kind of did a little bit. You have HCl is going to go to H plus plus Cl minus. That right there is showing the Arrhenius definition. Okay, so you're producing this proton, this free proton in water. Now, whenever we're talking about the Bronsted-Lowry acid, we're going to say, remember, something has to act as a donator. It's got to give a proton to something. And so when we write it this way, you can actually see that this proton can be donated to this oxygen right here. When it does, you have H3O plus. And then you have Cl minus. And some people say, well, wait a second, you have different things here and here. And no, you don't. And the reason why is, remember, this particular substance is aqueous. Because it's an aqueous substance, H plus aqueous just means it's an H plus plus an H2O, whereas that makes H3O plus. So these are the same thing. Now the last one that you have, it has to talk about the Lewis electron, or excuse me, the electrons. So you have HCl plus, we're going to draw it as HOH, which is water. Now remember, for a Lewis acid to be something, it's got to accept electrons. So what it can do is these electrons right here can actually go to this hydrogen right here. Now remember, a hydrogen can only have 2 electrons around it. So because of that, what it can do is it can take these 2 electrons and give them to chlorine. When it does, now you have chlorine with 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Now remember, chlorine has 6 and then this shared pair. So chlorine's happy because it meets the octet rule, and then hydrogen is now HOH plus, because what it's done is the oxygen on water has shared its electrons with that particular hydrogen. So you see you have the same products in all 3 definitions, just different interpretations of those particular rules. Next it says rank the acids below from the strongest to weakest on the pH scale. The greater that hydronium, the lower the pH, the stronger the acid. So first we have 1 molar HCl, which means I have 1 mole of H's, because remember, this will disassociate completely. So I'll have 1 mole of H pluses. When I do this, I have H2SO4. That's sulfuric acid. When it disassociates completely, though, instead of having 0.7, there are 2 hydronium ions associated with this. So because of that, it has a disassociation of 1.4 molarity. So the molarity is higher for sulfuric acid at 0.7 than it is at 1 for hydrochloric acid, based on the fact that there are 2 potential protons. And finally, you have phosphoric acid. Phosphoric acid is H3PO4, and when you look at H3PO4, you see that there are 3 potential hydronium ions to disassociate. So you can take this 0.5 and multiply it by 3, and that would give you a molarity of 1.5 molar for the hydronium ions. So because there are 3 available, you have to say, okay, well, that means that it's 3 times that concentration are available. So the strongest acid is going to be our phosphoric acid. The weakest acid in this particular case is going to be the hydrochloric acid. Now I need to talk about bases. Bases are generally thought of as the opposite of acids. Bases are bitter, they turn litmus paper blue, they conduct electricity, and they will neutralize acids, so they are electrolytes. Now Lewis bases, we have the same thing. We have a Lewis base, Bronsted-Lowry base, and we have an Arrhenius base definition. So we also have the Lewis base being the most broad definition. Now we did explore this a little bit, but a Lewis base is something that will donate electrons. So in this particular example, the ammonia is actually donating its electrons to this hydronium. It's giving those electrons to make a shared bond. Because of that, this is considered to be a Lewis base. Whenever you look at things in terms of a Lewis acid and Lewis base, you have to have both present in a chemical reaction. So you have this acting as the Lewis acid, and then you have a Lewis base. Okay. Likewise, when you have a Bronsted-Lowry base, it is a slightly more narrow definition, but it's still based on the transfer of protons. A Bronsted-Lowry base is defined as something that accepts the protons. So this original definition that we had, water is acting as the Lewis base, because it is the thing that is accepting the proton. Now the HCl is the Lewis acid because it's Bronsted-Lowry base and Bronsted-Lowry acid, because they are what are donating the protons and accepting the protons. Just like we had for Lewis, if you have one, you have to have the other. You can't have a chemical reaction in which you have something donate a proton, but not something that accepts that particular proton. Next, you have an Arrhenius base. The Arrhenius base is based on the reaction with water. So this is the one that's very, very different. Whenever you were to take a look at this, an Arrhenius base will increase the number of hydroxide ions when mixed with water. So when you take lithium hydroxide, it produces lithium and aqueous hydroxide. So this is the one that's very, very different. Now when we talk about bases, we're going to talk about the Arrhenius base. That's going to be our operational definition. Okay, so unless we say Lewis or Bronsted-Lowry, if I just say base, think of it in terms of the Arrhenius base. So the whole idea of all fingers are thumbs and not all fingers are, all thumbs are fingers, but not all fingers are thumbs argument comes up again. If you have a Lewis base, that does not necessarily mean that it's an Arrhenius base. If you have an Arrhenius base, that does mean that it's a Bronsted-Lowry base. Now here's some common bases that you see every day. You have acetone, which is generally used as a whiteboard cleaner. You have ammonia, which is used in a lot of cleaning products. You have calcium hydroxide, which is seen in, I think, milk of magnesia. That might be magnesium hydroxide. Lithium hydroxide is a very, very strong base that you'll see, along with sodium hydroxide. Those tend to be seen in a chemical laboratory. And you have pyridine, which is a naturally occurring base that you see in the body. So whenever you name bases, it follows the same rules as polyatomic ions. So you name the cation, then you name the anion, which is going to be hydroxide. So for example, if you were to look at it, you would say this would be sodium hydroxide. There are no special rules for naming bases. They follow the traditional polyatomic ion rules. There are only special rules for naming acids. Now you should be able to see this right here. You should see that our base is under assault. So if the cation is a transition metal, indicate the oxidation number. Whenever you're classifying bases, we do the same thing that we do with acids, is we actually define them by complete dissociation or partial dissociation. So you have weak bases that tend to be things like aluminum hydroxide, and then you have strong bases that tend to be things like sodium hydroxide. And then you have to memorize the strong bases as well. Now the strong bases are even easier to memorize than the strong acids, because they're all in the first two columns. If you look, you have the entire first period, first row, or first group, first group, and then you have part of the second group. So likewise, there are a little bit more bases than there are acids, but there are two main groups and it's fairly easy to memorize. So, ammonium, nitrogen trihydride, is a common base used in household cleaners. How would you classify ammonia? And if you look, ammonia is not on your strong base list, so you would classify it as a weak base. Next, it says write a balanced chemical equation for demonstrating calcium hydroxide as a Bronsted-Lowry base. So, whenever you have calcium hydroxide, you write it as CaOH, and then what you do is you have to have it react with something like water. Now whenever it reacts with water, you have to have something that donates the proton. So this right here will donate a proton to one of these. When it does, it produces an OH because it's given away its proton to calcium hydroxide. Calcium hydroxide is accepting that proton. As a result, this right here is the Bronsted-Lowry acid because it's giving away a proton. This would be the Bronsted-Lowry base because it's accepting that particular electron. So you would actually need two of these, and when you did that, you would get OH minus, but there would be two of them, and then you would also get calcium, 2 plus, and you would get water. Finally, we have a 250 ml solution of 1 molar hydrochloric acid is mixed with 300 ml of 0.4 molar barium hydroxide, and we want to know whether the resulting solution is going to be acidic or basic. So we know these things are both strong acids and strong bases, so we know they're going to disassociate completely. So because of that, we can actually look at the number of moles of each to determine whether it's acidic or basic. So what I'm going to do is I'm going to say this is 0.25 liters. I'm going to say this is 0.3 liters. I just converted the values. Now, whenever I look at the formula, molarity is equal to the number of moles divided by the liters. So if I take my molarity and I multiply it by my liters, I get my number of moles. So for each one of these things, I'm going to say 0.25 times 1, and that's going to give me 0.25. That right there represents my number of moles of hydronium ions. Because remember, we're going to work with the working definition of the Arrhenius unless we hear differently. Now next you have 0.4 times 0.3, but it's a little bit more complicated than this. Instead of it being just 0.4 times 0.3, you know that barium hydroxide is BaOH2. Because of that, for every barium you have 2 hydroxides, so you need to include the 2 term. Whenever you do that, you end up getting a value of 0.24. So whenever you do that, which one is more? You have more OH minuses or more H pluses, and if you were to look at it, you would still have more H pluses present. So this solution would be considered to be acidic, but because it only has 0.01 mole more, it is only going to be very, very slightly acidic. So you're looking to be, the pH is going to be very, very close to neutral. Now in your next presentation, you're going to actually investigate how acidic something is based on something called the pH scale.